All right. In our binary exponentiation problem, we learned that decision tree. So at that time, I drew some decision tree before. Okay? There are two different decisions based on the bit value. B sub I equals 0, the first decision. B sub I equals 1, the second decision. So you have seen that. In this part, we will consider a more general problem because this method can be applied to many other problems. But for the problem, we want to restrict ourselves to binary decisions. Two decisions, binary decisions. Decision 1, decision 2. So we will get a binary decision tree. Although definitely, so you can have more than two decisions, multiple decisions, but that will be too complicated. So for this class, we do not need to go that far. We just learned the binary decision type decision trees. Right? All right. General comparison sorts. First, let's look at the what is the comparison sorts? From the name, you can guess. Comparison-based sorting algorithm. So that's the comparison sorts. Comparison-based. So the main operation we need to sort our data is the comparison operation. So that's why we define that. We call it comparison sorts. Okay? All right. So let us study the comparison sorts. Now, the definition, so based only on comparisons between the input elements. Yeah. So let me explain this a little bit. Yeah. Otherwise, you may get confused a little bit. So when we look at the operations, so usually we have two types. So comparisons, assignments, right? Yeah. We need to do assignments. We need to do many assignments. Okay? But for comparisons, we know which one is smaller. So we have two cases, equal case and unequal case. For unequal case, one is smaller than the other. Okay? And this kind of information is very useful in our sorting. So we called comparison as the sorting operation. But for assignment, we assign one number to another, one value, one variable to another variable when we do this kind of assignment. So this operation, although we need it to arrange our data, but usually if you only use assignments, you cannot sort your data, right? Yeah. So you have to do the critical, important comparisons. So the role of comparisons and assignments are different in sorting. The role, okay? Assignments doing the supporting. The role is supporting type role. Comparison, that's the key type, key operations for the sorting. So they are different. Yeah. All right. So we say those operations that help gain order information, the sorting operation. Yep. Because when we do comparisons, we can get order information. But when we do assignments, we cannot get any order information. No matter how many times you do the assignments, you can never get any order information, right? Yeah. So they are different. Yeah. So the role, assignments, supporting, auxiliary, we use them to do the data arrangement. So, yeah. With this understanding, now we know the comparison. importance of the comparison. So that's why when we define our sorts, we base on this sorting operation. So comparison type, comparison sorting operation. Yeah. All right. There is another sorting operation we used before, counting also. So for integer data, counting operation can also be used as the sorting operation. The reason I explained in the counting sort, because the integer values and their positions, order positions, they have the natural relationship. So that's why the counting can be used as sorting operation for integer data. Right? All right. Now, so let us use the comparisons to build our decision trees. So decision tree model. Yeah. Here, we use decision tree as our analysis tool. So this tool, analysis tool. This tool helps us to solve the problem. We will use it to solve several important problems. Tool. It is powerful, a powerful tool. And we consider two-way decisions, binary decisions. So each decision has two possible outcomes. So we consider that. Right. The structure, if we have the binary decisions, when we construct a binary tree based on two decisions, we will get a binary tree. The binary tree we get called a full binary tree. Not a general binary tree. It is a special binary tree, full binary tree. What is a full binary tree? Okay, yeah. So we learned before, but so let's try to study another time. Yeah, full binary tree. Different from complete binary tree. We know complete binary tree, but full binary tree is different from. Do not get confused. Complete binary tree. Okay, all the levels complete. Okay, complete binary tree. All the levels are filled with the nodes. The full, not necessarily complete. So what's the meaning of full binary tree? Okay. This is a full binary tree. Okay. The definition is each node, either two child nodes or none. Two or none. In other words, there is no node with one child. Only one. The other missing. That is not a full binary tree. For full binary tree, each node must have two or none children. Okay? So that's the meaning of full. Two or none children. The definition of the full binary tree. Okay? Yeah. Nodes of a binary tree. All the nodes of a binary tree can be characterized into two categories: internal nodes and leaf nodes. Internal. So what are internal nodes? The nodes who have child nodes. Any node, if it has at least one child node, then it is an internal node. Okay. Then leaf nodes. Okay. We can also call it external nodes. So the nodes without any child node. Yeah, so you can see easily from the picture. Nodes with child nodes, nodes without child nodes. Yeah, these two different types. Yeah, we saw that before, but here we just, revisited this concept. But there is an important property between the number of external nodes and internal nodes for a full binary tree. Okay? So this property is only true for full binary tree. Okay? So for arbitrary binary tree non-full, it may not be true. It may not be true. Here, so I can remind you the heap. Heap is binary tree, right? Okay. Think about it. Is a heap full binary tree or not? The answer is not. Because for a heap, we can have one node with one child. The other branch empty. Well, we're allowed to have that. So a heap is not a full binary tree in general. Special case, it could be a binary tree, but in the general case, it's not necessary to be a full binary tree. All right, so that's the, the concept, basic concept understanding. Next, let us study a little more on the full binary trees. It has a simple property like this. Each internal node is full. Internal node must have at least one child. If it has at least one child, it must have two child nodes. So must be full. Okay? Yeah. So two child nodes. Complete. So this complete tree like this. So definitely complete tree must be always full, right? Yeah. And in this case, not full. See, this violation of the definition of full binary tree at this particular node. It is not full. Okay. Yeah. All right. Now we can look at a comparison-based decision. We make our decision based on comparisons. All right. Each decision, remember the binary type decision, 1, 2, the binary type. All right. Each decision has two outcomes. But you may ask, each decision should have three outcomes: less than, equal, greater than. Three different outcomes, right? So it does not follow our binary decision requirement. But we can merge. Can we merge equal and less than together? Less or equal? We can do that. If we merge those two cases, we can still sort the whole data array. No problem. Equal and less than, we combine them. Then we get a binary decision type. Yeah. So we define for every comparison, here we use this method to denote compare A and B. Short notation for comparison. Okay. Yeah. Two outcomes. The first one, A less than or equal to B. And the second one, A greater than B. Right? Binary decision. Okay? Yeah. Now we are ready to draw a decision tree. So for comparison sorts, we can draw a decision tree. Okay? Yeah. The question next: how to draw a decision tree? So I need to show you some simple example to see how do we draw a decision tree. Yeah. So let's look at that simple example. Yeah. But we will do that in our next part. B.3, we will see our first decision tree simple example.